last lecture we had talked about functions, and we saw how the use of functions can help us manage the task of solving complex problems and developing large and complicated programs to solve these problems. Today we'll discuss more about functions, but before that we'll start with a summary of what we had discussed last time. So here is how a function can be defined. You start with the return type of the function, which could be any of the types that we have seen so far. This is followed by the function name, and then within brackets we have to specify what are the parameters for the function. For each parameter we have to specify the name of the parameter and the type of the parameter. The parameter types can be again any of the types that we have seen so far, and then the entire function body is enclosed within braces, and which follows just after the function header. Usually the definition of any function should precede any call to a function in the program. So this really means that if the function f calls the function g, then usually it's better to place the definition of the function g before the definition of the function f. This is not always necessary, and we'll see later on why we may need to make exceptions to this rule, but at this point in time this is something we can always do. We also saw the return statement. The return statement has the purpose of specifying the value of the function execution, or as it is called, the return value of the function. So along with the return keyword we also specify an expression, and the value of the expression is what is returned to the calling function as the return value from the function. And also recollect that when within a function the return statement is executing, the execution of that function terminates immediately regardless of whether the function body has been finished or not, and control returns to the place where this function had been called from the calling function. So here is how we make a function call, that is how we use a function. So we specify a function name, the function that we want to call, and then for each of the parameters we have to supply a corresponding argument. The arguments must of course be of the right types, that is, the argument 1 must be of the type that is expected for the parameter 1, that is declared for the parameter 1, and similarly argument 2 must be of the same type as parameter 2, and so on and so forth. These arguments have to be expressions. They can be arbitrary expressions of the appropriate types, and this entire piece of code is treated by the C language as an expression, and this expression, the type of this expression is the same as the return type of the function that we are calling. This means that this entire expression can be used wherever a value or a variable, wherever a value of the type which is the same as the return type of the function is expected. For example, if the return type is integer, then this entire expression can be used wherever an integer is expected. Of course, as you know, you can also convert expressions into statements by putting a semicolon after them, in which case the value of the expression is discarded. The same is true for these kinds of expressions also. If you put a semicolon after such an expression, then it becomes a statement, and essentially the return value of the function is being ignored, and the only effect that the function call has in that case is the side effects that the function might have made. We haven't really discussed side effects in functions. We'll look at that in today's lecture. Okay, and then we talked about local variables in functions. A variable which is defined within the body of a function is said to be local to that particular function. And we talked about the scope and lifetime informally of variables. We'll talk more about scope and lifetime. By the scope of a variable we mean the portion of the program code where that variable is visible, so to speak, or where it can be used. So local variables are visible only within the function in which they are defined. So that's the scope of a local variable. And by lifetime we mean for how long does the variable exist, and the variable exists, a local variable exists only while the function is executing. We'll make these ideas more concrete with the help of some examples later on in the lecture. and parameters are similar to local variables in scope and lifetime, which means that a parameter acts just like a local variable. It is visible only within the function body. It is created when the function is called and is destroyed when the function returns. So what happens during a function call is that the arguments for the function are evaluated. Space is created for the parameters and local variables of the function which is being called now, as we saw in the last lecture, and then the parameters are initialized with the values of the corresponding expressions which are being passed as arguments, and then the function starts executing. When the function returns, the control returns back to the place in the calling function where the function was called. Note that we saw last time that if in some case the argument to a function happens to be a variable, and in the function body we happen to change the value of the corresponding parameter, then this change has no effect on the value of the original variable in the calling function when that function returns. Okay, let's now discuss the scope of variables a little more formally. So the scope of a variable is defined as the portion of the program where references to that variable are permitted. So as we have already seen, the scope of local variables extends to the body of the function within which the variable is defined, and the same is true for scope of parameters. The scope of a parameter to a function f is also within the body of the function f. So scope is a property of the program itself. That is, you can examine a program and demarcate portions of the code where a particular variable is in scope or is not in the scope, and so on. So we say that it's a static property of the program. The lifetime of a variable, on the other hand, is a dynamic property because it refers to the execution time of the program. So by lifetime, what we really mean is the time during which a particular variable exists, so to speak. So variables are created and they get destroyed. The time from the time when the variable was created to the time when it was destroyed is called the lifetime of the particular variable. For local variables and parameters, as we discussed last time, the lifetime is the time for which the function is active. Now, what do we really mean by a function being active? We have not really discussed this in detail in the last lecture. Let's do that now with the help of a simple example. Consider this program. So we have a function main with a local variable x. The function main calls a function f with some arguments which are not important for this example. Here is the definition of the function f. It has a local variable y and it calls another function g, and within g we have declared a local variable z. Now let's see the execution of this program on a timeline and see what is happening and when are variables getting created and destroyed. So this is our timeline. So when the function starts executing, as you know, the main function gets automatically called, and so when the main function gets called, the variable x gets created. So when at this point in time the function main has been called and the variable x has been created, now the function f is called from main. So f is called and y is created. Note that when f is called, the body of the function f starts executing and f is the currently executing function, but that doesn't mean that the main function is not active, because the function f has been called from main, and when main returns, execution will go back to main. So main is not finished yet, it is still active. So at this point in time the variable x still exists. It has not been destroyed, but because of the limitations of the scope, it cannot be accessed right now, because from within f the variable x cannot be accessed. The scope of the variable x is only the body of the function main. So within the function f the variable x cannot be accessed, but it still exists. So it has not yet been destroyed. So when the function f calls g, similarly the variable z gets created, and again the functions f and the function main are still active, because when g returns the execution will go back to f, and when f returns the execution will go back to main, and so the variables x and y, they still exist, though of course again they cannot be accessed from within the function g, because the scope of these variables doesn't include the body of the function g. So when finally G returns, at that point in time, the variable Z gets destroyed. So this is because the function G is finished, it is no longer active, and so the variable Z is destroyed, it doesn't exist. So the lifetime of the variable Z is this period during which the variable Z existed. And similarly, now the control has gone back to the function f, and finally the function f also returns, and at that point in time y also gets destroyed. So the lifetime of the variable y is the time from which f was called to the time when f returned. When main returns and the program actually terminates, at that time the variable x gets destroyed. So the lifetime of the variable x is the entire time for which the program was executing, because as long as the program is executing, the function main is always active. Okay, now what are the implications of this kind of a lifetime? Let's try to understand that using another simple example. So I have a program here in which the function main calls the function f twice, once with the argument 1 and once with the argument 2. Here is the body of the function f. The parameter is called x, and there is a local variable called y. So what happens in this function f? What happens is that if the parameter has the value 1, then y is assigned 10, otherwise it is not assigned anything, and then finally the value of y is printed. So now when f is called the first time, it is called with the parameter with argument 1, so the value of x is 1, so y gets assigned 10 and the value 10 gets printed. The question is, what happens when f is called again with argument 2? So in the second execution of f, is the variable y, which is not assigned any value in the second execution because x would have the value 2, what value would it print? So the answer really is that it is unpredictable. Let's see why that is unpredictable. So let's again draw the timeline and see how this program executes. So when main is called and then f is called, and at that point in time x, y are created. This is the first call to f, then y is assigned the value 10, 10 is printed, then f returns, x and y are destroyed. Now when f returns and control goes back to main, f is called again, and so x and y are created again. But because they have been created again, this means that this x and this y are not necessarily the same as this x and this y, even though they are the same variable of the same function. On a timeline, this x is not the same as this x, and similarly this y is not the same as this y. So now the y assigned 10 had assigned a value 10 to this y, but this variable has been destroyed and another variable which also happens to be called y has been created. There is no guarantee that the new variable y which has been created would be created at the same place where the old y also existed, and therefore there is no guarantee that this time the y variable y will retain its old value of 10. So what that implies is that the second output of this program is unpredictable. The first output will always be 10, of course, because x is given the value 1 and y is assigned 10, and then it is immediately printed. So the first output will always be 10, but the second output is unpredictable. So essentially the idea is that a local variable of a function does not retain its value across multiple calls to the same function. And that's a point that we have to remember. We cannot assume that the value that we assign to a particular local variable of a function, the variable will have the same value when the function is called again at some other place. Okay, let's now talk about variables which are known as global variables, and these variables differ in scope as well as in lifetime from the kind of variables that we have seen so far. The situation where we want to use global variables is one where we have a large number of functions which all need to access the same variable. Now, of course, one way of doing that is that you could pass the same variable as argument to all the functions. Now, that of course might make the program cumbersome, because for these functions the number of arguments may be very large, because the number of variables need to be accessed by a number of functions. So, in those cases, what you might prefer to do is to make these variables global, and making a variable global implies that the variable is accessible from all functions in the program. And to make a function global, what you need to do is to declare it outside any function. And that is, the declaration of the variable is not within the body of the function of any function, it is outside any function. And if we do that, then the variable automatically becomes global. Now, in terms of scope, the scope of a global variable is all functions or all parts of the program which appear after the declaration. That is, in the program, if we declare a global variable at a certain point, then below that point in the entire program, that variable is accessible everywhere. So, it differs in scope from local variables, because as you already saw, the scope of a local variable extends only to the body of the function within which the local variable is defined. And a global variable also differs from a local variable in the lifetime. The lifetime of a global variable is the same as the lifetime of the program. That is, it gets created when the program begins execution and is destroyed only when the program really terminates. So, the essential idea of the global variables then is that it's a variable which can be accessed anywhere in the program, because if you declare it right in the beginning of the program, then it's accessible everywhere below it, which means in the rest of the program, and remains in existence throughout the execution of the program. That is, regardless of which functions are called and which functions return and so on, this variable always exists and has the same value as what was assigned to it most recently. So, therefore, this variable can be used pretty much anywhere in the program. When we take up a large example of using functions to solve a complicated problem, we will see examples of global variables as well. Okay, but now with global variables, there can be a problem of overlapping scope, and what that means is the following: that there may be two variables with the same name whose scope may be overlapping. So, let us consider this example. So, here we have declared a global variable x. Note that this variable is declared outside the body of any function, and therefore it is automatically a global variable. And in this function f, we have declared also a local variable whose name is also x. Now, the scope of this function of this variable x is the entire program starting from this declaration downwards, and the scope of this variable x is the function body, which means this particular piece of the program code. So, now if you look at this portion of the program, this x as well as this x are in the scope. So, the question is, if we use the variable x within this part of the program, that is within the function body of the function f, which x are we referring to? Is it this x that we are referring to, or is it this x that we are referring to? So, the rule for that is that if there are two variables, both of which are in scope at a given point in time, at a given point in the program, then at that point in program, if a reference to that variable is made, these two variables have the same name, and if at that point in the program, if a reference to that variable is made, then the reference will always refer to the variable which has been declared innermost, or in other words, whose declaration is closest to the point of use. So, in this particular example, here is the reference to x. This is one candidate declaration and this is the other candidate declaration. This declaration is closer to this use of x, and so therefore, this reference to x really means this x and not this x. So, essentially the inner declaration hides the outer declaration within the scope of the inner declaration. Okay, let us now discuss functions in which we do not necessarily wish to return any value. So, in some cases we may not really bother about returning any value from the function. For example, we may only want to call a function for its side effects. The side effect might be to modify some global variable, or it might be, for example, to print something on the screen. For example, suppose we want to write a function which prints a given character a given number of times using a simple for loop or something of that kind. Now this function doesn't really have anything useful to return. So this function would not have any return type, and no return value would be returned from this function. So in such a case, what we could do is that we should declare the return type of such a function to be void, and again we'll see examples later on. Also note that within such a function, the return statement is not really necessary, because no return value has to be returned from the function, and the function will automatically return when its body is finished, that is, the execution of the entire body is finished. Of course, we can still have a return statement within such a function also without any return value specified. So the use of that would be that we want to return from the function prematurely or before the execution of its entire body is finished. We could do that by executing a return statement, and in the function of this kind, the return statement would simply be the return keyword followed by the semicolon. No return value would be specified. And similarly, we might want to define sometimes functions which don't have any parameters, and this might be required, for example, if all the information that the function needs to access is available as global variables. So in that case, again, the function would be declared as shown here. All you have to say is that there are no parameters, and so just put a void, the keyword void, where the parameters are expected. Okay, so let's end this lecture with a problem for you to think about. We'll not solve this problem in this lecture. We'll do that in the next lecture. So here is the problem. We want to write a program to find a path through a maze. So we are given a maze, and you must have seen puzzles of this kind in in popular magazines. So we are given a maze, and we are given an entry point through the maze, and there is possibly another exit point in the maze, and we want this program to find a path from the entry point to the exit point. And in some cases it is possible that there is no other exit point. So in that case, the path should bring us back to the entry point itself, and we should get out from the entry point itself. But if there is another exit in the maze, then the program should take us to that particular exit. So the maze is given as an input by the user, and the entry point is also given as an input by the user. So let's assume that the maze is represented as a two-dimensional grid of characters, where a star represents a part of the wall and a blank space represents an open space through which movement is possible. The maze is rectangular in shape, and at from any position in the maze, one can go in any of the four directions, provided that one does not run into a wall. So the entry point into the maze is also given by the user, and the path should take one from the entry point to some exit other than the entry point. And of course, if no other exit exists in the maze, the path should bring one out of the maze through the entry point itself. So here is an example maze for you to think about. So this is a 5 cross 5 maze. So there are 5 characters on the x-axis and 5 on the y-axis. For ease of convenience, we have labeled the two directions as x and y axis. So these stars represent walls in the maze, and these blank spaces represent open paths in the maze. So let's assume that the entry point is 1, 2 in the familiar Cartesian coordinate system. So which will mean that the entry point is this: x is 1 and y is 2. So, and here is another exit from the maze. So the path from the entry point should take us out of the maze through this particular exit point. So the path will look like, we start from 1, 2, which is this. When we go to 2, 2, which is this, so we move in this way. Then we go to 2, 3, this way. And then 3, 3, 4, 3, 4, 4, 4, 5, and then finally we come out of the maze here, which is 4, 6. So the algorithm for this problem is reasonably simple, but just think about this and you will find that even though the algorithm is simple, when you actually try to implement this, it becomes quite a bit complicated and one has to use several functions and so on. So we'll take up this example in detail and develop a program for this problem in the next lecture. In the meanwhile, please think about this problem.